Hello APC Mechanics students in Unit 5 Rotation, Class 10, Rotational Dynamics Part 2, Section 1, Acceleration of a Rolling Body Without Slipping. In Unit 2 we have seen the acceleration of different objects in translational motion under the influence of gravity. They can be summarized by the following table. Now, acceleration of translational motion, system versus acceleration. If the system is a free-falling object, which means we neglect a resistance, then the acceleration is g. Falling object on a smooth ramp inclined by theta, that would be g sine theta. An object moving down a rough ramp inclined by theta, that would be a into g sine theta minus mu k cosine theta. And here we should distinguish between moving down or moving up, because we know that friction is a contact force and contact forces are variable forces. And in case we're moving up, both friction and gravity are pointing down, which increases the magnitude of the acceleration, and it's given by g sine theta plus mu k cosine theta. Falling object of mass m under the influence of gravity and drag force, that would be a, is given by g multiplied by an exponential function, which is a decaying function. In this section, we'll investigate the acceleration under the influence of gravity of rolling bodies characterized by two variables of motion, translational velocity v, angular velocity omega. Here we're talking about rolling bodies in which they admit combined motions, translational and rotation. However, previously in Unit 2, we have only discussed translational motion. Mathematically, v and omega are independent. We distinguish between two cases: rolling with slipping, mathematically difficult to handle and requires the promotion of a system of differential equations. Let me clarify more. Now remember that in this case, for the falling object, under the influence of gravity, the acceleration a of the system have been determined by utilizing a differential equation, which v and a, the two unknowns or variables of motion, they are related to each other mathematically via calculus. Now, if our motion is rolling with slipping, which means we have two independent variables of motion, v and omega, this would require for us to solve not differential equation 1, but two differential equations. For this reason, I'm referring to system of differential equations, and this would be mathematically difficult to handle. However, we're gonna consider the more simpler case, which is rolling without slipping, in which v and omega are related, and we can make use of the following constraint equation, which is v is equal to omega r. For that, consider an object that can roll without slipping on a ramp inclined by theta. The moment we mention that the motion is rolling without slipping, this means we have static friction. Why? Because it is the force responsible for holding the object momentarily at rest at the point of contact with the ramp and eventually causing rotation. So here what I'm trying to point out is that rolling without slipping only happens due to friction. But which friction, static or kinetic? It's a bit confusing because the object is at motion, although it's at motion, but we're talking about this point, which is momentarily at rest when the object is rolling. So we're talking about static friction, and it is the force which is responsible for holding the body and prevents it from slipping. Now here we can talk about two accelerations, tangential and angular, and they can be determined via two different methods. And also I will represent at the end a method related to energetic approach. Now this object might be a hoop or a disc, for example. To generalize, so basically here the two different methods, at the end I will add another one, which is the third method using the conservation of energy, and I will clarify why here conservation of energy can be used although we have friction. Now to generalize our results, let's assume it's characterized by mass m and radius r and moment of inertia ICM around its center. Okay. Now, what is the first method? Via Newton's second law for rotation with a specific pivot point. Now, what are the forces acting on the object? Here in this case, in order to make use of Newton's law, we need to do a diagram of the forces. We know that we have two types of diagrams, FBD or a rigid body diagram. Whenever we're interested in the torque, we need to do a rigid body diagram in order to determine specifically the distance from the point of application of the force to the axis of rotation. Now we have the pull of gravity, and notice that we need to be careful by representing the pull of gravity at the center of the rolling object. So till this moment we don't know whether it's a hoop or a disc. We have the normal push. Remember that the normal push should be represented from the point of contact between the object and the ramp. The static friction and the static friction also should be represented from the point of application of the rolling object and the ramp, and here in this case the force of friction should be acting up the ramp because the object will be rotating in this direction. So the torque is, so the force, static friction, is producing a torque which rotates the body down the ramp. Now we're gonna choose the pivot point to be the point A, the point of contact between the object and the ramp, and notice carefully I have represented the point A on the diagram. Now apply Newton's second law for rotation, which is torque net is equal to I alpha, where I, here we need to pay attention, is the moment of inertia of the object about A. Now here, this is a mathematical relation, but also remember that tau net and I should be physically also related. Torque is affected by our pivot point, whether we choose it, for example, this point or this point or this point. So torque net would be affected. Because torque net is affected, I would be affected as well. And we know that the moment of inertia changes as we change the axis of rotation or the pivot, because remember that it's not only about the mass, but it is the mass distribution which causes inertia. Now, replacing torque net by the different forces that produces the torque given by the pull of gravity, normal push, and static friction, here we can directly eliminate the normal push and the static friction, because we're working about the torque net about the pivot point A, and both static friction and the normal push, they don't produce any torque because they passes through the pivot point A. And we're left with the pull of gravity. Now, in order, so okay, consider the clockwise rotation to be positive along the direction of motion. Now that would be the radial direction, that would be the tangential. If the ramp is inclined by theta, then as we know that this is theta, and that would be pi by 2 minus theta. And the torque produced by the pull of gravity, so let me erase this. Now notice that the pull of gravity about the pivot point, it will try to rotate the object in this direction, which is considered to be the positive direction according to our assumption. For this reason, we consider it to be positive torque. And R is the distance from the pivot to the point where the pull of gravity is applied, which is this distance. For this reason, I stress on the fact that the pull of gravity should be represented correctly using a rigid body diagram. And if this is the tangential and that's the radial, then cosine of this angle, and that would give us mgr sine theta. Now replacing mgr sine theta in the Newton's second law, now we need to apply the parallel axis theorem. Why? Because I, which represents the moment of inertia, it's the moment of inertia of the rolling object about the point A. However, what's given is ICM, which is the moment of inertia of the object around the center. And we know that I at A could be related to I at the center of mass using the parallel axis theorem by adding a counter term, which is mr squared, which represents m is the mass of the object and r is the distance from A to the center. Now replacing it in the previous expression and knowing that alpha is A over r, now whether we determine alpha or A, they are both perfectly the same. Alpha represents the angular acceleration and A represents the linear or the acceleration of the center of mass or the tangential acceleration. And we're interested in determining A, so here A is the only unknown. Now notice carefully here what we're gonna do. So you can think about it in this way. R is down, we can make it up, so that would be to the power of 2, and this cancels. Now here again we can divide by r square, by r square, by r square. So this with this would cancel, and this with this would cancel, and we're left with mg sine theta equals I, the center of mass, divided by r square, plus m A over r. Now here we can also simplify by m, simplify by m, simplify by m, so this becomes 1, and this will cancel. Now why we're doing that? Because the moment of inertia has a dimension of kilogram meter square, so we can, if we divide by mr square, so we make it a dimensionless quantity which can be added to 1. Now dividing by m, we're left by that. So the acceleration a would be given by g sine theta divided by ICM over mr square plus 1. Then the acceleration of the rotating object is given by the following expression, and the angular acceleration can be determined from a by knowing that a is given by alpha r and replacing it here. Then if we move r down, we would have that alpha is equal to g sine theta divided by r into ICM mr square plus 1. Now we expand here, so g sine theta over ICM, that would be mr plus r. So that would be the expression of the angular acceleration. Now, what are some particular cases? If the rolling object is a hoop of moment of inertia, I, the center of mass, is equal to mr square. So what do we have? The acceleration would be, then mr square and mr square, they would cancel. 1 plus 1 would give us 2. That would be half g sine theta. And if the rolling object is a disk of moment of inertia, half mr square, if we do the same calculation, we're gonna have that it's given by 3 over 2 g sine theta. And notice that here, the acceleration of objects that are less inertial is greater, and we will elaborate on that at the end of this section. Now this result can be determined again by choosing the pivot point to be the center of the rolling object and the combination between different Newton's laws. So let's investigate that. Second method, via Newton's second law for rotation with a specific pivot point, choosing the pivot point to be the point B instead of A, the center of the rolling object. So now we have moved from A to B, and we're gonna apply again in Newton's second law for rotation. Tau net is equal to I center of mass multiplied by alpha. Now why here in this case the Newton's second law is given by the I of the center of mass? Simply because our choice is the pivot point to be B to be the center of mass. Now I'm referring to the center of mass, which is the geometrical center of the body, because we're assuming uniform mass distribution. That would be the torque produced by gravity, normal push, the friction is equal to ICM multiplied by alpha. And here notice that two forces, they don't produce torque, the pull of gravity and the normal push, because both the line of action passes through the center. So we can directly eliminate them, and we're left with the friction and choosing the clockwise rotation to be the positive direction. Now what is the torque produced by the static friction? Now notice that this force produces torque in the positive direction assumed, and it's being tangentially applied multiplied by distance r. So for this reason it's positive, no need for an angle, and it's the force multiplied by the distance. Replacing it in the equation, we would get the following. But here notice carefully, we have two unknowns, static friction and alpha. One way to deal with this problem is to promote it to a differential equation. However, Fs and alpha, they are not related mathematically. One of them is force, the other is alpha. So in order to solve for this, we need another equation, and this can be determined by applying Newton's second law for translation. F net is equal to ma net, which is the pull of gravity plus the normal push plus the static friction is equal to ma net. Now projection along the direction of the x-axis. Now here no need to do an FPD again, we can make use of our rigid body diagram. We know that in such type of problems, and if the acceleration is downward, the x-axis is chosen along the ramp itself. Now what are the forces that have projections? Now the normal push has no projection, that would be 0. Now Fs would be minus with no angle because it's in the negative direction. What about the pull of gravity? It would be plus Fg multiplied by cosine pi by 2 minus theta, and we're left with the following equation. Mg sine theta minus Fs is equal to ma, and we're interested in determining Fs. So in this case, if we isolate Fs, that would be Mg sine theta minus ma. And we will replace this equation here, because we're interested in determining A. Alpha can be directly changed into A by utilizing that alpha is A divided by R. Now we have the two following equations. Replacing Fs here, we would get the following. And we know that alpha is A over R. So alpha can be converted to A. Now here we'll perform the same trick. So what we're gonna do is the following. So this is a combined fraction, R can be shifted toward ICM, so that would be mg sine theta multiplied by R minus mRA is equal to I center of mass divided by R multiplied by A. Now this is up, we can take it down, so that would be to the power of 2. We can divide by the mass, so here we have the mass. Then we have G sine theta minus A is equal to ICM over MR square multiplied by A, and we can take A to the other side. And we factor out A, and again we have the same result. Then the acceleration of the rotating object is given by A, which is G sine theta divided by ICM over MR square plus 1, which is the same result. Again, the same result can be achieved from an energetic approach. Although friction exists because the type of motion is rolling without slipping, however, energy is still conserved, and this is very important. Friction, so what is the role of friction here? Friction prevents the bottom of the object from slipping, and the point of contact is not displaced, and this is very important. Now, we stressed previously that as this object is rolling, this point is momentarily at rest, and it's not being displaced. And we know that the force, whether in the integral form or the product form, the work, whether it's in the integral form or F times D, if the displacement is 0, then the work done by the force itself is 0. So momentarily the work by this static friction is 0. And what does it mean that the work done by friction is 0? So the friction itself is not dissipating energy. Because the point of contact is not displaced, 0 displacement, then friction performs no work and no energy dissipated, because we know whenever we're asked about the energy dissipated, it means that we need to calculate the work done by friction. Then luckily enough, although we have friction, but friction in this case performs no work, and we can still apply the conservation of energy safely. Assuming that the object starts rolling from rest, take the PE level to be the horizontal plane passing through the center of mass at the bottom of the ramp. Now remember that we know the gravitational potential energy is given by mgh. We didn't elaborate much about this in Unit 3 because all the objects that we are interested in have no dimensions. Now the object has a dimension, and they are represented by rigid by the diagram. H represents the distance from the PE level to the center of gravity of the object. So for this reason, we're assuming that the PE level to be the horizontal plane passing through the center of mass at the bottom of the ramp. So we can take the PE level to be here or here, but the more precise one, if we need to make the GPE or the potential energy gravitational to vanish, we need to make it passing through the center of mass. However, one choice can be also to be taken at the bottom of the ramp. But here, if you take the PE level to be the bottom of the ramp, you should also start by measuring the height from the bottom of the sphere. Okay. Now apply the conservation of energy. Energy initial is equal to energy final. So initial kinetic energy plus initial potential energy gravitational is equal to kinetic energy final plus gravitational potential energy final. And that would be 0 because we're starting from rest, and that would be 0 because at the bottom of the ramp, the center of mass of the rolling object would be passing through the PE level, and we're left with mgh is equal to half mv square plus half I center of mass omega square. And here notice carefully, the kinetic energy is not only translational but also rotational, because we have a combined motion, so we should not forget this term. And whenever we're talking about rotation, we're talking about the rotation of the center of mass, because here we have split the two types of motion. Previously we were doing a combined motion and we taken the pivot point to be the point A. That's fine. And Newton's second law for rotation has been promoted for torque net and I to be around the pivot point A. But here, whenever we're talking about energy, we forget about shifting this pivot point, and whenever we're talking about rotational kinetic energy, it's just due to pure rotation around the center of mass. And here notice that h is taken to be the distance from center to center. In some problems you can define h to be from rim to rim. That's fine, that works. It only depends on how you define your h. So the basic idea that if h has been measured from top initially, so the final state you need to measure it at the top, because there is an additional distance that should be taken, which is the size of the object. So one way to do it, for example, is if you started measuring h from the point A, then also at the final state you need to measure h from A. If you measure it from the bottom, which is B, also you need to measure it from B. However, a rule of thumb always to consider measuring the distances from the center of the object, or as stated in the exercise itself. And now here we're interested in determining V. We know that omega, so remember that we're interested basically in determining A, but A can be deduced from V. So let's unify V and omega using the constraint equation, which is given by V is equal to R omega, and that would be as follows. Now again, we will use the same trick, which is representing I, but not I, but rather I over mr square. So here we have divided by m, divided by m, divided by m. So these will cancel, and r square can be combined with the moment of inertia. And here we have a factor of 2 down, so we'll take it up. And we're gonna read the equation from right to left or left to right, factoring out v square. Then v square would be given by 2gh divided by the following fractional expression. And the translational speed, or the speed of the center of mass of the rolling object at the bottom of the ramp, is given by the following. And the acceleration can be determined from kinematics using the equation v square is equal to v square initial plus 2a delta x. And sine theta would be h over delta x, which means delta x is h over sine theta. So here remember that because this is a horizontal and this is a horizontal, so this is theta as well, and delta x would be the distance traveled along the ramp, that would be delta x. So sine theta in this case would be h over delta x, so opposite over hypotenuse, which means that delta x is given by h divided by sine theta. Now, because initially at rest that would be 0, so we're left with ax, which is v square over 2 delta x. Now v square is 2gh over that, and delta x is given by h over sine theta. We can cancel 2 with 2, and we can cancel h with h. Sine theta is down, so remember that if we have a over b over c over d, this is given by a over b times d over c. We're using the rule here, so sine theta becomes up. 2 will cancel with 2, so we're left with g sine theta over 1 plus ICM over mr square. Then the acceleration of the rotating object is given by the following, which is the same result. And here let me do the following interpretation. So we have determined using 3 different methods, 2 for Newton's law and 1 for the energetic approach, and we have found that the speed at the bottom of the ramp is given by the following, which is a modified 2gh and a modified g sine theta. Now notice that the moment of inertia in each case it's found in the denominator, and you can notice that as I increase, because it's found in the denominator, as the body becomes more inertial, the speed at the bottom of the ramp decreases and the acceleration decreases as well. For objects that roll without slipping on a ramp, if the moment of inertia is greater than the acceleration is smaller. If the moment of inertia is greater than both the linear and the angular velocity is smaller. So here I also should say both accelerations, tangential and angular. Okay, so as we're trying to say, as the body becomes more inertial, the acceleration on a smooth, rolling without slipping on a ramp, both the acceleration and the velocity would be smaller. And now for the rest of the video, we're gonna solve a problem. A thin hoop of mass m and radius r and rotational inertia mr square is released from rest from the bottom of the ramp of length L. Above, the ramp makes an angle theta with respect to the horizontal tabletop to which the ramp is fixed. The table is at a height h above the floor. Assume the hoop rolls without slipping down the ramp and across the table. Express all algebraic answers in terms of the given quantities and fundamental constants. Now whenever we determine expression, we need to make sure it's being expressed in terms of m, r, l, theta. Okay. In part A, derive an expression of the acceleration of the center of mass of the hoop as it rolls down the ramp. So here we have different methods, first method, second method, third method. I would go with the first one to utilize a rigid body diagram entangled with Newton's second law for rotation about a pivot point A, which is the point of contact between the rolling object and the ramp. The forces acting on the object would be the pull of gravity, the normal push, and the static friction. Choosing the pivot point to be the point A, applying Newton's second law for rotation. Here you need to pay attention that torque net would be around the point A. and I would be the moment of inertia of the body about the point A. We have the moment of inertia or rotational inertia, which is given by mr square about the center of the hoop, so we need to apply the parallel axis theorem, where I is the moment of inertia of the object about A. Now that would be the torque done by gravity. Normal push static friction is equal to I alpha. Consider clockwise rotation to be positive along the direction of motion. That would be the tangential, and radial, and that would be the tangential. That would be theta, that would be pi by 2 minus theta. So, and here we're interested in determining the torque produced by the pull of gravity, assuming that the pull of gravity, so if this is the positive direction, then the pull of gravity is trying to rotate the object in this direction, producing a positive torque. The magnitude of the force is mg. The distance from A to the center is given by r, and cosine of the angle between the force itself and the tangential direction is pi by 2 minus theta, and that would be mgr sine theta. Now always think about sine theta, because also at the table that we stated at the beginning, if an object is sliding on a smooth ramp, the acceleration is given by g sine theta. So basically sine, which plays the role, and not cosine in this case. And now applying the parallel axis theorem, which is I center of mass plus mr square. Now why? Because remember that here I is the moment of inertia about the pivot point A, but how can I for the pivot point A be determined from I, the center of mass, by applying the parallel axis theorem and adding mr square? So that would be given by the following. Now remember that here the trick that we always apply, which is given by I, we need to represent I in the form of I divided by mr square, but here no need to apply this trick because already we know what is I. I, the center of mass, is given by mr square. So first let me also say that alpha is A over R, and I is given by mr square, so we replace it here. And now we can do the cancellation effect. M with M cancel. Now these R with R cancel, and R with R would cancel, and we're left with the following expression, that A is given by half g sine theta. Then the acceleration of the center of mass of the hoop as it rolls down the ramp is given by A is half plus multiplied by g sine theta. Now in part B, they're telling us to derive an expression for the speed of the center of mass of the hoop when it reaches the bottom, and this can be determined by utilizing kinematic equations, which is v square x is equal to v square x 0 plus 2ax delta x. Now the initial speed is 0. That would be v square multiplied by 2 multiplied by half g sine theta multiplied by L, and v would be given by radical gl sine theta. That would be the speed of the rolling object or the hoop at the bottom of the ramp. Now in part C, they're telling us to derive an expression for the horizontal distance from the edge of the table to where the hoop lands on the floor. So upon reaching this point, the hoop will be launched and it will hit the floor somewhere here. Now here, because the tabletop is horizontal, which means that theta is 0, making cosine theta to be 1, making sine theta to be 0. So we're gonna use the equation which is x is x0 plus v0 cosine theta t, and make use of theta as 0, cosine theta is 1, sine theta is 0, knowing that x is d. So here d is not given. I'm referring to d. Also, before I continue, let's make sure of parts A and B that are being expressed in terms of the fundamental constants and the given. So indeed g and theta, indeed g, L and theta, which all of them are given. Now x0 is 0, cosine theta is 1. So we're interested now in finding time, and time can be found by referring to the vertical component. Now y is y0 plus v0 sine theta t minus half gt square. Why here do we have the minus sign? To indicate that the positive direction is chosen to be up. In this case, sorry, that's a mistake. It should be minus h, which is y0 to be 0, and that would be 0, which means that minus h is minus half gt square, which means that h is half gt square, having the times radical to h over g. Then d is v0 t. v0 have been determined from the horizontal and t from the vertical, combining them together, simplifying g with g, and we're left with the following. And here you can make sure of the dimensional analysis. This is meter and meter, which give us meter square, and radical square root of meter square would give us meter. Sine theta and 2, they have no units. That would be the distance covered by the hoop when it reaches the ground. And finally, in part D, they're asking us, suppose that the hoop is now replaced by a disk. So what is the difference between the hoop and the disk? The disk is less inertial than the hoop, having the same mass and radius r. How will the distance from the edge of the tabletop to where the disk lands on the floor compare with the distance determined in part C for the hoop? So here, notice that so the horizontal distance covered here depends. So the horizontal, so if you remember that D is given by V multiplied by T. So if V increases, then the distance D will increase eventually. Now the distance D here covered by the hoop upon being launched depends how much speed we have at this point. Alright, and here we're comparing two types of objects, a hoop and a disk, and we know that the disk is less inertial. So if we replace the hoop by a disk, upon the disk reaches this point, it will have more speed compared to the hoop. For this reason, if we're talking about the disk here, if it reaches this point, the speed would be greater, which makes the distance covered to be greater. So in this case, our choice would be greater than, and we're gonna say that the disk has a moment of inertia less than that of the hoop. Then the linear speed of the disk at the bottom of the ramp is greater. Then the disk will cover a larger horizontal distance than that of the hoop, because simply the speed of the disk at this point is greater than that of the hoop, which makes the horizontal distance covered greater. And that's it for me in this video, guys. See you soon in a new one.